Good day, class. Today we're going to go over a couple of small things, the last things of the unit. We're going to talk about finding determinants of matrices first. All right, and we will do determinants of 2 by 2 matrices by hand, but anything larger than that, we are just going to use a calculator, so no need to worry about these minors and cofactors here. All right, so the definition of the determinant of a 2 by 2 matrix. So the determinant of the matrix A, all right, and this is a 2 by 2 matrix here, all right, so we just kind of label the entries A, B, C, D. These will just obviously be numbers, all right. So the determinant of matrix A, which you can also write as essentially, it looks like the absolute value of matrix A, all right, is equal to AD minus BC. Right, so if you see this, right, if matrix A is A, B, C, D, so if you just see the bars around it and not the full brackets, right, then that actually is signifying that we're trying to find the determinant. But all you have to do is A times D and subtract B times C, right, and that's how you find the determinant of a 2 by 2 matrix. So pretty straightforward, fairly easy. All right, so let's look at some examples here. It says to find the determinant of each matrix. All right, so this would be A, B, C, and D. All right, so the determinant of matrix A, which this is how you would see me write it, all right, is equal to A times D minus B times C, which in this case is going to be 2 times 2 minus negative 3 times 1. Right, so that's going to be 4 minus negative 3, or 4 plus 3, which is 7. And that's it. That's all we have to do. So here, the determinant of matrix B. Right, we do the same thing here. AD minus BC. So here we would have 2 times 2 again, minus 1 times 4. So 4 minus 4, this would be 0. All right, here we can also find the determinant of matrix C. So here we will have 0 times 4 minus 3 halves times 2. All right, so this is going to be 0 minus 3. So that's simply negative 3. All right, so determinants of 2 by 2 matrices, very straightforward, right? Not really a whole lot of difficulty there. All right, this is to help find determinants of matrices larger than 2 by 2s, but we're only going to use calculators for this. All right, so find, well, skip that here. All right, again, we're not worrying about minors or cofactors, so we will simply use a calculator. So if we want to find the determinant of this matrix A, all right, all we have to do is input our matrix here. So we're going to edit matrix A. This is a 3 by 3 matrix. We have 0, 2, 1, 3, negative 1, 2, 4, 0, 1. All right, so now we can simply quit out of our matrix window here. We can say, okay, we go back to our matrix options. We go over to math. The very first entry here, 1, is that DET. That stands for determinant. So I hit enter here. I go, and that just takes it out to my main calculating screen of my calculator. I go back to my matrix menu. I've already edited my matrix A, so I have what I want in there. We just hit enter there. All right, and this this will give us the determinant of matrix A. All right, so this is simply the determinant of matrix A, according to our calculator, is 14. Okay. We can try again. All right. Well, we can go back to our matrix menu. We can edit our matrix. This is also a 3 by 3. So we have 3, 4, -2, 3, 5, 0, -1, 4, 1. All right, so we can click back out. I'm just going to cheat a little bit here and say second enter, and that will just bring up the determinant of matrix A, and I have edited A to be what I want it to be. So -31. So we know from our calculator that the determinant of this matrix A is equal to -31. All right, so pretty straightforward, pretty cut and dry. That's really all we're doing with determinants, right? So if it's a 2 by 2, all right, then we go ahead and use our formula, AD minus BC. All right, if it's anything larger than that, 3 by 3, 4 by 4, then we just go ahead and use our calculator. All right, do note that you can only find determinants of square matrices, which means to be square, you have to have the same number of columns and rows. Okay. So the other thing that we're going to look at today, all right, we're going to look at inverses of matrices. All right. Again, if it's just a 2 by 2 matrix, then we will find the inverse by hand. Anything larger than that, again, we'll go ahead and use our calculators. All right, we're also going to be able to use inverse matrices to solve systems, right? Just like we solve systems using Gaussian and Gauss-Jordan elimination, there's a way to use inverse matrices to do it as well. Okay, so the definition of the inverse of a square matrix, all right? So do note again that you can only find the inverse of square matrices. So our definition here says let A be an n by n matrix, and let I sub n be the n by n identity matrix. And we identified the identity matrix a few days ago, last week sometime, I believe. That's a matrix, a square matrix, where the main diagonal, which means from the top left corner to the bottom right corner, are all ones, and every other entry is a 0. Right? So if there exists a matrix, A to the negative first power, which means A inverse, right, such that A times A inverse is equal to the identity, and A inverse times A is also equal to the identity, then A to the negative first power is called the inverse of A. Okay, so so show that B is the inverse of A. All right, and remember here that what our definition just said is that you have to be able to multiply these things. And remember that matrix multiplication is not commutative, so A times B doesn't necessarily equal B times A. However, when they are inverses, right, it doesn't matter. Whichever way you do it, you will get the identity matrix. All right, so let's go ahead and first multiply A times B. All right, now these are both 2 by 2 matrices. So since these are equal, we can multiply them, and our answer will be a 2 by 2 matrix as well. All right, now if we forget how to do matrix multiplication, remember whatever entry we're looking for. In this case, this would be 1, 1, so first row, first column. Remember, I always take the row from my first matrix, and I take the column from my second matrix, All right, and then I go ahead and multiply respectively and add. So -1 times 1 plus 2 times 1. Well, this is -1 plus 2, so that equals 1. All right, so we're good there. All right, now, all right, I'm here. So I'm still first row, but now I'm second column. All right, so when we go ahead and do that, we will get -1 times -2 plus 2 times -1. So that is 2 plus -2, which is 0. All right, the next entry down here is row 2, column 1. So I go row 2, column 1, and when I go ahead and multiply these out, all right, we're going to get -1 times 1 plus 1 times -1. I'm sorry, just 1 times 1. So there we get -1 plus 1, which equals 0. All right, and finally, our last entry here is row 2, column 2. So I'm already at row 2 here. I go column 2 over here. All right, and now I get -1 times -2 plus 1 times -1. That is 2 plus -1, which is 1. All right, so when we multiplied these things, we got the identity matrix. Remember, the diagonal, main diagonal is 1s, and everything else is 0s. That is what we have. So since this is the identity matrix, all right, I can say that B is equal to A inverse. I could also say that A is equal to B inverse. It wouldn't really matter. All right, but it asked up here to show that B is the inverse of A. So that's what we did. All right, we can do the same thing here. I'll go a little bit faster here instead of actually going through every little step-by-step process. All right, so of course a 2 by 2 and a 2 by 2 we can multiply, and we will get the 2 by 2. So here, first row, first column, I'm going to get -2 plus 3, which is 1. First row, second column, I'm going to get -2 plus 2, which is 0. Here, second row, first column, we're going to get +3 plus -3, which is 0. And here, second row, second column, we're going to get 3 plus -2, which is 1. So again, we got the inverse matrix. So B is equal to A inverse. And we're done. All right. I'm not going to go ahead and really, this isn't too huge of a deal here, but this is just very mathematically technical. So when a matrix A has an inverse, A is called invertible or non-singular. Otherwise, A is called singular. A non-square matrix cannot have an inverse. Right? So I mentioned that earlier. All right. To find the inverse of A, try to solve the matrix equation A times X is equal to I. All right. Again, I'm not really going to worry about you using this equation. All right. There's going to be a quick little formula for a 2 by 2 matrix to find the inverse, and anything else, anything larger than that, we're just going to go ahead and use our calculator. So let me get to, here we go. All right, this is the formula to find the inverse of a 2 by 2 matrix. So again, if I have some matrix A, which is 2 by 2, and we'll call those entries A, B, C, and D, just like we did when we were talking about the determinant. All right, A is invertible if and only if AD minus BC is not equal to 0. All right, if you remember, AD minus BC is what we just talked about earlier. That's called the determinant. All right. So if AD minus BC is not equal to 0, then the inverse is given by 1 over the determinant times D negative B negative C A. All right, so from our original matrix A here, we flip A and D, and we negate B and C. We don't flip them, we just negate them, right? So the B and C stay there, we just make them negative. The A and D, however, change places. All right, so let's go ahead and, oh, we already have this done for us here, but we'll go ahead and start that over. All right, so here first what I want to do is find my determinant of A. All right, so I have AD, which is 3 times 2, minus B times C, which is negative 1 times negative 2. All right, so this is 6 minus 2, which is 4. All right, so since that is not 0, we can find our inverse. All right, and our inverse is going to equal 1 over the determinant, which I just found, which is 4, times, remember I switch my A and my D, so this will become 2, this will become 3, and I negate my B and my C. I don't switch them, I just negate them. So this will become positive 1, and this will become positive 2. All right, and once we go ahead and remember this is just scalar multiplication, so I multiply every piece in here by 1/4. 1/4 times 2 is 1/2. 1/4 times 1 is 1/4. 1/4 times 2 is 1/2 again. And 1/4 times 3 is 3/4. So there is my inverse matrix. All right, we can try B here. So if we do the determinant of B, all right, we do AD minus B times C. So we get 6 minus 6, which equals to 0. All right, so since our determinant is 0, there is no inverse here. So B is what we call singular. All right, and that's it. All right. And this is another way in which we can solve systems of equations using inverses. All right, so if A is an invertible matrix, then the system of linear equations represented by AX equals B has a unique solution given by X is equal to A inverse of B. All right, so this is the important part here. All right, A, we need to know, is the coefficient matrix. All right, so it's not the augmented matrix that we use to solve them by hand when we use Gaussian and Gauss-Jordan elimination. All right, it's just the coefficient matrix, which is only the coefficients, so only the numbers in front of the variables. All right, and B here is going to be the constant matrix, which is a matrix of just the constant numbers, just the regular numbers that come after the equal sign when our equations are in standard form. All right. So then, of course, we can actually just plug, once we plug these into matrix A and matrix B into our calculator, we can just tell our calculator to do this, and it will give us all of our answers. Now, this is matrix X, but typically, if we're looking at a 3x3 system of equations, then matrix X would be like XYZ. If we're looking at a 4x4, it would be XYZW. Right. We'll get to that here in a minute. Okay, so let's look at this example. All right, so if we make matrix A our coefficient matrix, so that's just 1, 1, 1, 2, -1, 2, and -1, 3, -2. So that's our coefficient matrix. And B, of course, is the constant matrix, which is just the numbers after my equal sign here. So 2, 1, -2. Right? We know that X is equal to A inverse times B from our last slide there. Okay. Now it is important to note that X is our variable matrix, which in this case would just be X, Y, Z. Okay. So we can actually let our calculator do this for us. So if we go back to our matrix menu here, we're going to edit matrix A. It is a 3 by 3. 1, 1, 1, 2, -1, 2, -1, 3, -2. Okay, now we want to go back to our matrix menu. Oops. And we want to edit matrix B, which matrix B is this matrix here, and that is a 3 by 1 matrix. So we have 2, 1, -2. Alright, so now if we quit back out to our main screen here, alright, we can go ahead and say, alright, well, we hit enter on matrix A. We can hit x to the negative first power there to make that A inverse. And then we're simply multiplying that by, go back to our matrix menu, go down to matrix B, hit enter there. So A inverse B, and it gives us -3, 1, 4. So over here we say, okay, x is equal to -3, 1, 4. And of course, we know that the variable matrix is x, y, z. So that's saying that x is -3, y is 1, and z is 4. So if we wrote it as our ordered triple, right, that would be our solution. All right. One other thing that I do want to show you. Okay, so if we want to find the inverse of a larger than a 2 by 2, remember we have that nice formula for a 2 by 2, but if we want to find the inverse of a larger matrix, we can just go here. All right, we can edit matrix A. It's a 3 by 3 again. So we have 1, -1, 0. Messed up there. 1, -1, 0, 1, 0, -1, 6, -2, and -3. Alright, so now we can go ahead and quit out here. I can just go back to my matrix menu, hit enter on A to bring it out to my main screen, hit this x to the negative first button, and hit enter. Alright, so there is my inverse matrix. So here I can just say, okay, well, A inverse is equal to -2, -3, 1, -3, -3, 1, -2, -4, 1. All right, so our calculator can do that very nicely for us as well. Okay, so just a recap of some of the things that our calculator can do. All right, yesterday I showed you how our calculator can put matrices in row echelon form and reduced row echelon form. All right, today we talked about how to use our calculator to find the determinant of a matrix and the inverse of a matrix. And then we also used our formula x is equal to A inverse times B to very quickly and easily solve systems of equations. All right. So that is all for this unit. I will go ahead and put an assignment up on Delta Math that covers determinants and inverses. That will be it for the unit. Then we will just have the review and the test on Friday. Have a good day.